in which all the angles are right angles. And both of these two categories are all parallelograms, which are quadrilaterals with two pairs of parallel sides. And then finally, we have these two outside groups right here. So the first one are trapezoids, and these are quadrilaterals with exactly one pair of parallel sides. And kites have two pairs of equal length adjacent sides. And all of these make up quadrilaterals. So our first example is to prove that the sum of the interior angles of any quadrilateral is 360 degrees. So let me start out by drawing a quadrilateral. And let's draw the diagonals. Okay, but we can just draw one. So we know that the sum of the interior angles of any triangle is 180 degrees. So we see that if we just sum up all of the interior angles of triangle ADC, then triangle ABC, we get the sum of the total angles of the quadrilateral. So since the sum of these are 180, the sum of the interior angles is just 360. So the key was just to draw the diagonal and notice that it splits the quadrilateral into two triangles. So we also, in this example, will also show an inequality that can be useful regarding quadrilaterals. So basically, if a quadrilateral has side lengths A, B, C, and D, then we have that A plus B plus C is greater than D. So let's just draw on the diagonal. Oops, actually, this is C, and this is D. So this is just diagonal, and we'll call it E, and then we'll call this A, B, C, and D. So if you guys remember the triangle inequality, it says that the sum of two sides of any triangle is always greater than the third. So if you look at triangle ABC, from the triangle inequality, you get that A plus B is greater than E. Now, if we apply the triangle inequality to triangle ADC right here, we get E plus C is greater than D. So now we can combine these two inequalities by adding C to the first equation. So that gives us A plus B plus C is greater than E plus C. Oops. It's greater than E plus C. And from the second inequality, we know that E plus C is greater than D. So we have A plus B plus C is greater than D. So now you guys can try the following checkpoint, which should test your understanding of the quadrilateral inequality. If you guys have any answers, you guys can just post it in the chat. Okay, we'll start now. So basically, Joy wants to make a quadrilateral with rods with side lengths 3, 7, and 15, and some other length rod. So let's call that rod X. So 3, 3, 7, 15, and X. And what are our constraints? X has to be between 1 and 30, and X cannot be equal to 3, 7, or 15 because it says she has exactly one of every integer length. So now let's use the quadrilateral inequality. So one way we can take the sum is 3 plus 7 plus 15 is greater than X. That's one of our inequalities. Now, another one of our inequalities can be looking at the 3, 7, and X side lengths. So that's 3 plus 7 plus X is greater than 15. Now notice that the other two possible ways we can do it don't really matter, since we'll have a constant on the right-hand side that is less than one of the terms on the left-hand side, so it's basically useless inequality. So if we simplify these, we have 25 is greater than X, and X is greater than 5. So X can be from 6 to 25, but keep in mind, X cannot be 3, 7, or 15, so that rules out two of the possibilities from this, namely 7 and 15. So the number of, this is actually 24. So the number of entries in this range is 19, but we have to minus 2 because we can't have a rod of length 7 or 15. So that's just equal to 17. So in this problem, it's important that you keep track of like your inequalities being strict and the fact that there's only one rod of each size. So next we'll be going over parallelograms. So a parallelogram is a quadrilateral with exactly two pairs of parallel sides. So we can see that these pairs of parallel sides cannot be adjacent because that would contradict them being parallel. So here's an example of a parallelogram, because we have these two sides are parallel and then these two sides are parallel. So now we'll look at some of the important properties of parallelograms. So the first one says that any two adjacent angles of a parallelogram are supplementary. To see why, let's draw a diagram. Oops. This A, B, C, and D. And we want to look at this angle and this angle. So if this angle is X, then since AB is parallel to CD, we can extend AD upwards, and this is X. And since this is a line, this has to be 180 minus X. So now the second part says that opposite angles of a parallelogram are congruent. So let's draw a new diagram. And then in this diagram, we'll also draw the diagonals of the parallelogram. So by this side being parallel to this side, we have that if this angle is X, then this angle is X. And looking at the other pair of parallel sides, if this angle is Y, then this angle must be Y. We can see this by just noting that each of the diagonals is just a transversal with respect to one pair of parallel sides. So this angle is just x plus y, and this angle is also x plus y. So we see that the opposite angles are congruent. And you can do the same argument to see the other pair of opposite sides are also congruent. So now the third part of this theorem says that the opposite sides of a parallelogram are in fact congruent, so they have the same length. So to see this, you may remember last week we did similarity and congruence. So we'll be using ASA congruence right now. So what we want to show is that triangle ABC is congruent to triangle BCD. Now, how do we show that? Well, from the previous theorems, we know that if this angle is x, then this angle is x. If this angle is y, then this angle is y. And now they both share the same side, which is diagonal BD. So since they share two angles that are separated by a common side, we have that they are congruent by angle side angle congruence. So this in fact holds. So what does this mean? This means that AB is congruent to CD and AD is congruent to BC. The fourth property is that the diagonals of a parallelogram bisect each other. So here we'll use ASA congruence again. If we have A, B, C, and D, if we draw the two diagonals, and say they intersect at some point E, then by parallel lines, if this is X, then this is X. And if this is Y, then this is also Y. So, and they also share this angle in common, but they also share AB and CD by the previous property that the opposite sides are congruent. So triangle EDC is congruent to triangle EAB by ASA, where the angles are Y and then this side and then X. Actually, if you want to be more precise, you can say EBA so that the sides are corresponding. So anyways, from these congruences, we get that ED is equal to EB and EA is equal to EC. So this again shows that the diagonals bisect each other or divide each other in half. Finally, our fifth property is that the sum of the squares of the sides is equal to the sum of the squares of the diagonals. To see this, we'll look at the following diagram. So if we look at figure 1.1b, we see that if we draw these altitudes, we can get an expression for AD and BC in terms of using the Pythagorean theorem. So, and then if we just plug all of these into 5, then it should all work out. I'll save you some of the details. So finally, we want to find the area of a parallelogram. So let's look at this parallelogram right here, ABCD. If we chop off triangle ADE, and paste it on the other side, so we move that triangle right here, then we get this figure right. We get this figure right here, which is just a rectangle. So the area of this parallelogram is just equivalent to the area of this rectangle. Now, if you remember how to find the area of a rectangle, it's just the product of two adjacent sides. So the base times the height. So the base of this rectangle is AB, and then the height is just AE. So the area of this parallelogram is just AB times AE. So in general, for a parallelogram, we call AE the height, and we denote it by H, and we call AB the base, similar to a rectangle. Okay, now we'll try this example. So in triangle ABC, we have AB is equal to AC is equal to 28, and BC is equal to 20. Then we have points D, E, and F on AB, BC, and HC, so that DE and EF are parallel to AC and AB. What is the perimeter of parallelogram ADEF? So first let's draw a diagram. So it looks like we have an isosceles triangle because two of the lengths are the same. So let's call this A, B, C. So BC is 20, AB is 28, AC is 28. And then points D, E, and F are on these sides such that D, E, and EF are parallel to AC and AB. So let me draw. I think the problem is saying something like this. If this is D, this is E, and this is F, then we have DE and EF are parallel to AC and AB. So yeah, this is correct. So then it's asking the perimeter of parallelogram ADEF. So first, we want to see if we can find any similarities between the triangles in this diagram. So one thing to see is that triangle ECF is similar to triangle BCA. Why is this true? Well, we know that this angle is equal to this angle by parallel lines, and similarly, this angle is equal to this angle, and this angle is this is just common angle. So yeah, we get that these are similar by AAA similarity. So then we have that ECEF is an isosceles triangle since BCA is also an isosceles triangle. So ECF is isosceles. So that means that EF is equal to FC. So now, so how do we find the perimeter of ADEF? EF is just FC. So basically, since the opposite sides are equal, the perimeter is just equal to 2 times AF plus FE. But what's AF plus FE? We know that FE is just FC. So this is AF plus FC. And AF plus FC is just AC. But in the problem, we're given that AC is 28. So this is just 56. So if you just look at this problem, the fact that BC is equal to 20 is completely irrelevant. Now let's do this example. So a parallelogram has 3 vertices at 2, 1, 4, 2, and 7, 7. And the problem is asking us to find the 2 possible points for the other vertex of this parallelogram. So first, let's plot this on the coordinate axes to give us a geometrical idea of what's going on. So 2, 1, that's one vertex. 4, 2, and 7, 7. So it's asking us to find the 2 possible locations of the 4th one. So let's call this point A, this point B, and then this point C. Now, let's see if we can use the fact that opposite sides are parallel, and that they're congruent to each other. So now, to do this, if you remember, to determine whether 2 lines are parallel in the coordinate plane, they have to have the same slope. So let's calculate the slope of AB. It's just a rise of 1 and a run of 2. So the slope is just 1/2. Now, CD also must have this same slope. So D must either be at 5, have x coordinates of 5, or at 9, because this has a rise of 2. So now I'll save you some of the arithmetic details, but we know that D has to have x coordinates either 5 or 9, because the line between A and B has a run of 2, and and we want to find the y coordinates such that the line between C and each of these has slope 1/2. And if you do these calculations, you find that the values of y for the point having x coordinate 5 is 6, and then the other point must be 9, 8. So these lines, so essentially how we found these points is that CD must have the same length as AB, and then AB must be parallel to CD. So these turn out to be our two possible locations for point D. So yeah, this is our answer. Now you guys can try this checkpoint. Okay, so let me give you the solution. So essentially, uh, the problem is just outlining a parallelogram for us. So this is the curb, and this is like you have the two stripes here on the side. So it says that has parallel curves 40 feet apart. So this distance must be 40. And then a crosswalk um, crosses it at an angle. So this is basically the distance between the crosswalks we want to find. And it says the length of the curb is 15 feet. So this is 15. And we know that the length of each stripe is 50 feet. So now we want to find the distance between the stripes, which is just this. So let's think about this problem in terms of the area of the parallelogram. If we just look at the what they've given us, we can see that the area of the parallelogram is just 40 times 15, which is 1600. Why? Because this is a base and it has length 15, and then this is the height, which has length 40. So the area is just the base times the height, which is 600. Now let's look at the height from the other base height pair, in which the base is the stripe. This should be equal to 50 times h, where h is this distance, because the areas using two different base height pairs still give us the same area. So solving for h, just get h is 12. So next we'll be discussing rhombi, which is a plural of a rhombus. So a rhombus is just a parallelogram in which all the sides have the same length. So if you draw it out, it looks something like this. This is a little weird, but I think it works. So this side is parallel to this side, and this side is parallel to this side. So the diagonals of a rhombus are perpendicular. So if you draw the diagonals, this is a right angle, and the diagonals bisect each other. So basically, say the diagonals have length a and b. So so if this is a over 2, and then this vertical part is b over 2 and b over 2, then the area is AB over 2. Why is that? Well, if you look at each one of these individual triangles, since it's a right triangle, the area is just 1/2 times its two legs. So 1/2 times A over 2 times B over 2. But we have 4 of these right triangles in our rhombus, so we multiply by 4. So if you do this, you just get the total area is AB over 2. So next, let's do this example. So it asks to find the length of a diagonal of a rhombus, which has one side of length 10 and one of the diagonals of length 12. So let's draw this out. Oops, this is little. So we know the diagonals bisect each other. So it has side length 10, so all of these are 10. And one of the diagonals is 12. So let's say this vertical diagonal is 12. That means this is 6 and this is, oops, this is 6 and this is 6 because they bisect each other. So now notice that if we just look at this triangle just have a right triangle with hypotenuse 10 and one leg 6. Oops. And one leg 6. So if you remember, this is just like a 3, 4, 5 right triangle. So 6, 8, 10 is just a times 2 scale of that. So the other side is just 8. So this is 8. This is 8. So they're asking the length of the other diagonal. That's just 8 plus 8, which is 16. The next example, it's asking us to find the area of a rhombus with side length 6 and one angle being 60 degrees. So it says the side lengths are 6 and there's a 60-degree angle. So this is 60. Now, if we just look at the triangle to the left of this vertical diagonal, so like this triangle right here, we see that it's an equilateral triangle. Why is that? Because the two legs are the same, and the vertex angle is 60, which means this must be 60 and this must be 60. And the other side is also the exact same equilateral triangle. So the rhombus is just comprised of two equilateral triangles with side length 6. So if you remember the formula for the area of an equilateral triangle, it's root 3 over 4 times the side length squared. So in this case, we have root 3 over 4 times 6 squared. And then we have two of these equilateral triangles that are making up our rhombus. So this would be our answer. So just simplify this. This comes out to 18 root 3. Okay, next we'll be looking at squares and rectangles. And if you, we're covering these sequentially. So squares and rectangles are just parallelograms and rhombi. Or a square is a rhombi. So the official definition is that a rectangle is a parallelogram with all right angles. And the area of a rectangle with width A and height B is AB. So why is that? If you just draw it out like this AB, AB, you have all right angles here. Let's draw this diagonal. Then we split the rectangle into two right triangles, each of which has area AB over 2. Each of which has area AB over 2 because A and B are the two legs. So the area of the rectangle is just 2 times this, which is equal to AB. And then a square is a rhombus. So a rhombus being a parallelogram with all 4 sides equal, with the stipulation that all its angles are right angles. So essentially, a square is just a rhombus that's also a rectangle, as you might recall from a Venn diagram. And so from this, we see that squares are rectangles, but keep in mind that rectangles are not squares. So the area of a square is just s squared because A and B are the same. So now we'll try this example. So a square ABCD with side length 12. We have a point E lying on the square, so that E is 3 units away from AB and 5 units away from AD, and it's asking for the length of EC. So let me draw it out. So it's saying the square has side length 12. Now that these are all right angles. and we have a point E such that E is 3 units away from AB and 5 units away from AD. So it would be something like this. And then it's asking the length of EC. So asking the length of this. So let's drop down these perpendiculars. And since each of these are rectangles, we know that this length is 5 and this length is 3. So this has to be 7 and this is 9. And since this side is parallel to this side, we have this is also 9. So EC is a right triangle with side lengths 9 and 7. So the hypotenuse is just square root of 9 squared plus 7 squared, which is the square root of 81 plus 49, which is the square root of 130. Okay. Now we'll discuss a useful theorem that comes up frequently in competition math. It's called the British flag theorem. So basically, if we have a point P inside of a rectangle, ABCD, then AP squared plus CP squared is equal to BP squared plus DP squared. So let's draw this out. Say we have like a point P here, and then we draw AP, CP, DP, and then BP. And it's saying that AP squared plus CP squared is equal to BP squared plus DP squared. So when you see the squared of these side lengths, you should immediately think of the Pythagorean theorem. So let's see how we can get some right triangles here. Let's draw the perpendicular from P to each of the sides. Like so. And let's call these X, Y, C, and W. So now we can get some equations. Since we can get X, we know that this distance is X. You know, this distance right here is W. This distance right here is Y. This small distance here is C. This is X. This is Y. Then this is W. And right here it's C. So now we apply the Pythagorean theorem to the right triangles with hypotenuse AP, BP, CP, and DP. So if we look at this triangle right here, you get that x squared plus w squared is equal to AP squared. Now looking at this triangle here, we get x squared plus y squared equal to BP squared. Now if you look at you can look at this triangle right here. So that gives us x squared plus y squared is equal. Wait, no, never mind. I already did that. We already did BP. So let's look at this right triangle right here. We have y squared plus c squared is equal to cp squared. And then finally, if we look at this right triangle right here, we get w squared plus c squared is equal to dp squared. Now let's add up AP squared and CP squared and then BP squared and DP squared. So we have AP squared plus CP squared is equal to x squared plus w squared plus y squared plus c squared. And then BP squared DP squared is equal to the same thing. Squared plus w squared plus y squared plus c squared. Hence, AP squared plus CP squared is equal to bp squared plus dp squared as desired. So we've just proven this. So now you guys can try this checkpoint. Okay, let's go over this checkpoint. So basically we have this diagram I just drew here. So a circle is inscribed in a square, and then a square is inscribed in that circle, and then a smaller circle is inscribed in this smaller square. And then the problem is asking for the ratio of the area of the smaller circle to the area of the larger square. So in ratio problems, it might be useful to just set one of your variables to be a constant. So in this case, let's just set the radius of the smaller circle to be 1. So by this, we have that the area of the smaller circle is just pi. Now, now let's look at the area of the smaller square. You know that this is 1 and this is 1. So the smaller square has area 2 squared, which is equal to 4. Now, let's find the area of the larger square. So if you know that this is 2, and then as you might suspect, this is just this triangle right here is just a 45, 45, 90 right triangle. That's because the square is the smaller square is just centered at the midpoints of the larger square. So if this is 2, then we know that this must be root 2 and this must be root 2. So the side length of the larger square is 2 root 2. Therefore, the area of the larger square is 8. So then the final answer is just pi over 8. Okay, now we'll go over trapezoids. So a trapezoid is a quadrilateral with exactly one pair. So that's important. It's exactly one pair of parallel sides. So now let's do this example. Where basically, if you look at a trapezoid, if you draw the diagonals, you get a handful of congruent angles just like a parallelogram, because the diagonals act like transversals to the parallel sides. So in this example, we have AB to be 20, and then base CD to be 30. So CD is 30. Now, we draw in diagonals AC and BD, and then they intersect at X. So if the area of trapezoid ABCD is 300, what is the area of BXC? So how do we do this? So we look at the height of the trapezoid. So so we know that this is 30, and we can find the height because if you don't remember, the area of a trapezoid is 1/2 times the average of the base, or 1/2 times the sum of the bases times the height. So we have that we have 300 is equal to 20 plus 30 over 2 times h. So this implies that h is equal to 12. Now, to find the area of BXC, we can just find the area of AXB or ACB minus the area of AXB. So the area of BXC equal the area of ABC minus the area of AXB. So how do you find the area of each of these? ABC has base 20 and has height h, but we found h to be 12. So the total area is 20 times 12 over 2. And then AXB, now it's time to use similarity. So since the bases, we know that by drawing these diagonals, that this angle is equal to this angle, and this angle is equal to this angle. And since they both share this angle, ABX is similar to CXD. So now using the similarity, we have the base of AB is 20 and the base of CD is 30. So the triangles are in a 2:3 ratio. In other words, the CXD triangle is just a 50% magnification of the AXB triangle. So that means the height of this triangle should be 50% more than the height of this triangle. So if we let this height be x, then this must be 1.5x. So we have x plus 1.5x. That should be equal to h, which is 12. So 2.5x equal to 12. X is equal to 12 over 2.5, which is equal to 4.8. So we found the height of triangle AXB. So we know that it has base 20. The area is just 20 times 4.8 over 2. So 20 times 12 over 2 is So 20 times 12 over 2 is 120. And then 20 times 4.8 over 2 is just 48, because these two cancels and you have a 10 times plus. So our answer is just 20 minus 48, which is equal to 72. So now we have a theorem for trapezoids. So basically, this is a trapezoid, and basically the mid segment of a trapezoid is just located halfway in between the two bases. So by that we mean that this distance is equal to this distance, and this distance is equal to this distance. And equivalently, by similar triangles, this distance is equal to this distance. So it's basically right in between. And yeah, the area of a trapezoid with base, or I don't know. Actually looks more like a. There we go. So the area of a trapezoid with bases A and B and height h is just 1/2 h times a plus b. Uh, we're we're running a little short on time, but the gist of one way you can prove it is just by extending these two legs up to a common point, and then the area of the trapezoid is just the area of this big triangle minus the area of this small triangle. You can find both of them using similarity. Okay, now you guys can try the following checkpoint. Okay, I'll just go over this problem now. So basically, the problem is asking for the area of EFCD in this following diagram. So, and 12 is the altitude. So basically, by similarity in the mid segment, EF is just a mid segment. So we know this height is 6, and we know that EF is just the average of the two bases. So that's just a plus 20 over 2, which is 14. So the area of EFCD is just the average of the bases, which is 14 plus 20 over 2, times the height, which is 6. And that is okay. I'll just skip this checkpoint since we're running a little short on time. Okay, finally, our last special quadrilateral is called a kite. So a kite is basically just a quadrilateral with two pairs of equal length adjacent sides. If we draw it out, it'll look something like this. Similar to a rhombus, its diagonals are perpendicular to each other. And this longer diagonal bisects the smaller diagonal. So this length is equal to this length. So if we let D1 and D2 be the lengths of the diagonals, we get that the area is equal to 1/2 D1 D2. It's not hard to prove. You just let this be X, and let this be D1 minus X, and just find the area of each of the four right triangles separately and add them up. So let's do this example. So we have parabolas y is equal to ax squared minus 2, and y is equal to 4 minus bx squared over 2, or 4 minus bx squared, and they intersect in exactly 4 points on the coordinate plane. And the problem says that these 4 points are the vertices of a kite of area 12. We want to find A and B. So let's look at the y-intercepts of these. So the y-intercept of this is -2. The y-intercept of this is 4. you can find these by substituting x is equal to 0. So from these, we know that this is one vertex of the kite at 0, -2, and another vertex is at 0, -4. So one of the diagonals has length 6, or 4 minus -2. Now to find the since we know the area of the kite is 1/2 times d1 d2 is equal to 12, and we know d1 is 6, we can find d2, and we find that d2 is just we find that d2 is 4. So now we can plug in y is equal to 0 into both of these parabolas, and then we can solve for a and b. And it turns out when we do all this arithmetic, we get that is equal to 0.5 and b is equal to 1, giving us a plus b is equal to 1.5. Okay, finally we have this problem. So basically, this person has a small kite and a large kite. So the small kite is drawn on this 1-inch grid. And then for the large kite, he triples both the height and the width of the entire grid. So essentially, let's find the area of these. So the area of the portion that's left off here is, so this triangle has area 2 times 3, which is 6. This area has 2 times 3 again, 6 is 3 times 5, which is 15. And this one also should have 15. So the amount wasted on the small kite is 30 plus 12, which is equal to 42. Now, let's look at the dimensions of the large kite. The small kite has dimensions this is 7, and this is 6. So the large kite has dimensions 3 times that. So large kite is 21 by 18. So the area of the kite is just the product of the diagonals, which is 21 times 18, which is equal to 378. And then so by multiplying, 378 is the area of the foil that she uses to cut the large kite out of. And then the area of the kite is just 1/2 times d1 times d2. So just 1/2 times 378, which is equal to 189. So the amount that's wasted is 378 minus 189, which is equal to just 189, since this is half. Okay, I think that's it. We can take a 5-minute break now, and then we can start a Kahoot.
Okay, so we'll start the Kahoot at 3:10, and just another reminder.
I'll get the Kahoot. Oh, you go.
Oh yeah, just another reminder that registration for the Iowa City Math Tournament is still open, and that instead of having a math circle meeting next week, we encourage you to participate in the tournament instead. And more details are available on our website. Kevin?
Yeah, so I'll get the Kahoot ready right now. We will start in a few minutes. Wait, just curious, who is the square? Are we all in? Anyone start to A rectangular tile measures 3 inches by 4 inches. What is the fewest number of these tiles that are needed to completely cover a rectangular region that is 2 feet by 5 feet? Nice job. Reclaiming title is actually number 1. Nice. Question 2, here we go. The diagonals of a rhombus are 6 inches and 8 inches. What is the perimeter in inches of the rhombus below? like a good amount got it correct. I just want to say, if you got 32, you calculated the area of the rhombus instead. And if you got 40, that is because you probably mistaken the diagonals, half the diagonals is 6 and 8, which gets you a side of 10, which is not correct. If you get a side of 10, then you would get a perimeter of 40. And that is unfortunately not correct because you have to take the diagonals by 2. Divide the diagonals by 2. And Rip reclaiming title. But Smiley Face is number 1 now. In the diagram, the area of rectangle PQRS is 24. If Q equals TR, what is the area of quadrilateral PTRS? Nice job, everyone. And I'm dumb is actually number 1 now. How many square units are in the area of the pentagon shown here with side lengths 15, 20, 27, 24, and 40 units? Y'all did really good. And Smiley Face is back to number 1. In this diagram, the area of rectangle ABCD is 40. What is the area of MBCN? actually did pretty well. If you answered 30, you accidentally calculated the area of AMND, which is actually has an area of 30. Actually, not 30. Yeah. And smiley face is still number 1. Nice. The ratio of 2 interior angles of a parallelogram is 4:5. Find the measure of the parallelogram's obtuse angles. So looks like we should talk about this problem. So a parallelogram has a bigger side and a smaller side, and they both equal to 180. And if the ratio is 4:5, that means we can set the x to be one part of the ratio. So we can do like 4x plus 5x equals 180. Then we can solve for x, and that would be x equals 20. So if x equals 20, then the interior angles would be 80 and 100 degrees, and the obtuse angle would be 100 degrees. So that is the correct answer. I wonder how 4 people got 110. And we have smiley faces, still number 1. Nice. What is the area of a rhombus with side lengths square root 89 units and diagonals that differ by 6 units? I'll give you a hint. Try to find 2 integers whose squares will add up to 89. So the main thing here is when I try to look at this problem, I see square root 89 is 64 plus 25, and that is 8 and 5. 8 squared, 64, 5 squared, so that's 25. So we have 8 and 5, and because those are just half the diagonals are going to be 16 and 10, which do differ by 6 units. So we can take 16 times 10 divided by 2 to get 80, which is our correct answer. Who is drawing on the screen, by the way? Oh. And we have smiley faces going in. It's still number 1. The angles of quadrilateral ABC satisfy angle A equals 2 angle B equals 3 times angle C equals 4 times angle D. What is the degree measure of angle A rounded to the nearest whole number? Did someone forget to round down instead of up? Because I see a lot of people just put 174. Just curious. Also, who was drawing the top right? Those are just my extensions. Anyway, so what I would do here is, no, you cannot actually set angle A to be X, angle B to be 2X, 3X, 4X. You cannot do that. The best way to take it is you have angle A, you can set it to 12X, angle B to be 6X, angle C to be 4X, and angle D to be 3X. So, oh my god, what are you drawing? Anyway, so basically you can solve for X and then multiply it by 12 to get around 173. There you go. Oh jeez. And I'm dumb is actually number 1 now. In this figure, ABCD is a rectangle and AZ equals WC equals 6 units, while AB equals 12 units, and the area of trapezoid WCD is 120 square units. What is the area of triangle BQW? The blue button in the right corner says. Oh. Anyway, let's go over this problem. So we have ABCD is a rectangle with AZ equals WC. So this is 6. AB is 12 units. So the first thing I will try to look for is try to find the lengths of ZD, which we can do by finding the because we already know the area of trapezoid ZDCW. So we can find ZD by taking ZD plus WC divided by 2 times DC equals 120. And that would result, so because AB equals DC, so DC is 20, that means ZD plus WC is 20. So that means ZD is 14. So we have ZD is 14. That also means BW is 14. So 14 times the Q to BW is actually half of DC because Q is the midpoint of DB. So we have the area would be 14 times 3 divided by 2 or 21. Wait, how is, what? Thought it was, okay. And someone is drawing a Kokichi, nice. Oh my gosh. Okay, moving on. And the rankings have stayed. One angle of a parallelogram is 120 degrees and 2 consecutive sides have lengths of 8 and 15 inches. Find its area. Ooh, 60 squared root 3. Yeah, 60 squared root 3 is the correct answer. I think if you got 30 squared root 3, you probably only calculated the area of one triangle if you divided the parallelogram into 2 if you try to calculate the area. Koik, number 2, nice. In parallelogram ABCD, AB equals 38 centimeters, BC equals 3 to the y cube, 3 times y cubed centimeters, BD equals 2x plus 4 centimeters, and AD equals 24 centimeters. What is the product of x and y? we got 34, which is correct. Yeah. Ooh, conic is number 1 now. Nice. The consecutive angles of a particular trapezoid form an arithmetic sequence. If the largest angle measures 120 degrees, what is the measure of the smallest angle? Also, can we please not write over the actual problem itself? Thank you. Wow. Most of you got it correct. Working table is number 3. Number 2. And we have %. It's actually pretty decent. Yeah. Anyway, I'm gonna hand this screen back to Reese now. Good job, everyone.
Okay. Thank you for coming. Remember to register for the Iowa City Math Tournament if you haven't already, and also submit your problems for the exercise leaderboard. And have a good week. Send us questions if you have any. Oh yeah, there will be prizes. Okay, now it's time to see who is AFK.